Hello everyone, welcome to our second circuits video. This is one of the simple circuit components known as a capacitor. I mentioned it earlier in the video series. It is one of the three simple circuit components, which are capacitors, inductors, and resistors, not including the wire itself, although the wire acts as a resistor, as we learned from the resistance video. So let's take this and work with it. So given the voltage, epsilon naught, the area of each plate, and the separation between them, what is the charge on each plate? And the note that I added is in the formula Q equals CV, which I believe you have in your formula sheet, Q is for each plate. So we can work this out given our known formulas, Q equals CV and Q equals epsilon naught A over D, and get what we need. So we know epsilon naught is a constant. We know A and D, so we have C. So let's start by writing that down. So we have epsilon naught A over D equals C. We also know that Q is equal to CV. That's something that we know. Now we can plug this in for C, and we also know V, so we know Q. So this is a relatively short problem, so Q is equal to epsilon naught A over D times V. So that was pretty painless. These two work out the same, so this is pretty simple. If we want to discuss something important about this so that we always know whether we need to square something or whether we need to understand what's going on, let's think about the units on this. I want to do a little more digging into what the units are for current and circuit questions, because I feel like that's something that gets lost in the fray. So we have Q, which is in units of coulombs, right? We have V, which, if we want to work this out, V is KQ over R, which is KQQ over R squared in newtons, times R over Q. So we get newtons times distance over Q, which is equal to joules per coulomb. So that means that volts is in units of joules per coulomb. Okay, so now we can work out capacitance. Capacitance is given by Q equals CV, or C equals Q over V. So let's work that out. We have C is equal to, and we just worked out Q and V, so we have coulombs over joules per coulomb, which is equal to coulombs squared per joule. Okay, so we've worked out what a capacitor's units are from knowing what we know from Physics 1 and knowing what potential is. So this is a relatively powerful method of thinking about things. We want to, when we're working with circuits, there's a lot of new units that we haven't heard of before. You know, we have potential, we have field, we have coulombs, we have amperes, which are really just units of current. So let's think about one other formula, which I'm sure you've seen at this point, and let's think about the units on that one so that we can get a little bit of intuition about what's going on here. So we have, and this is Kirchhoffs Law. It's called, I believe, a couple of other things, but I learned it as Kirchhoffs Law. So we have V is equal to I R. Let's pick this apart a little. We get volts, which is in potential. Those are the same thing. Volts and potential are the same thing. We get current, which is in coulombs per second, and we get resistance. And we want to work out what the units are for resistance real quick. And we can even bring that back to this formula. R equals R naught 1 plus alpha T minus T naught. So we can work that out real quick and understand what's going on here. So just to start, we've got joules per coulomb is equal to coulombs per second times x. So just multiplying this fraction over, we get joules seconds over coulomb squared. So joules seconds are a unit that will pop up again in physics and again and again and again and again. This is action. This is pretty close to the units you'll see in a lot of quantum mechanical quantities. But so this is the units of resistance, right? So this is the units of resistance. Joules times seconds over coulomb squared. And this is sort of unintuitive. Why, what is that saying? It's energy times time per charge. But the longer you think about it, the less interesting it is. So let's move on to thinking about how this affects this. So we get that 1 plus alpha times T minus T naught and I'm going to write that up here. We get R naught times 1 minus alpha times T minus T naught is equal to resistance. So we actually see that this has units of resistance, and this has units of resistance, and we can put this roughly in units of joules, though that's a little bit iffy, but I'm going to, relate joules and Kelvin. So we'll call this joules seconds per coulomb squared is equal to 1, because this is joules seconds per coulomb squared, times some units times joules. So we can look at this and say that alpha must be seconds per coulomb squared and various other units. Depending on how we want to frame T. T can be in Kelvin, in which case it is not exactly equivalent to joules. T is an interesting concept in that it's not the same as energy, but it can be derived almost identically from energy. And if you all are looking for a really great resource for these sections, I would recommend Isaac Asimov's, and I think I said this in an announcement, Understanding Physics. And especially his sections on circuits, resistance. He was a famous science fiction author and an astrophysicist. And what his book does so much better than most other books, though it's a little dry, is that it is kind of funny. He's got a kind of funny sense of humor. And it doesn't throw you in head first. He walks you through the history of each discovery, who did what, how they discovered it, why they discovered it. And he does it in an interesting way, and in a way that makes it sort of fun and easier to learn. I highly recommend this book. You can order a copy online for $5 or something. It's old, it's cheap. All right, thank you, everyone.